Good afternoon, everyone. I'm Baiwen from the Department of Chemical Engineering and Materials Science in the University of Minnesota. I would like to talk about our recent progress on the nonlinear model predictive control of flexible ammonia production. So ammonia is a chemical that is widely used across multiple areas and is now the second most produced chemical in the world. Nearly all ammonia synthesized today is through the Haber-Bosch process, requiring roughly 60% of global hydrogen production. And over 96% of this hydrogen comes from oil, coal, or natural gas, with the remainder 4% from electrolysis. And even among this hydrogen from electrolysis, only 1/3 is powered by renewable energy. So due to this high dependence on fossil fuel, ammonia production now contributes to about 2% of the total carbon dioxide emission. To decarbonize the agriculture and energy sectors, green ammonia production is considered as a key pathway because it is a carbon-free process where the renewable energy source is used from wind and solar is used to power air separation for nitrogen production and power water electrolysis for hydrogen production. This nitrogen and hydrogen are further used in the Haber-Bosch process for ammonia synthesis. And conventionally, the ammonia produced in the Haber-Bosch process is at a constant production rate, and there isn't much flexibility in changing the production rate. However, these renewable energy sources are usually intermittent, resulting in intermittent nitrogen and hydrogen production. So to buffer this intermittency, large storage units for nitrogen and hydrogen are required in the green ammonia production, which makes the whole process prohibitively expensive. On the other hand, the flexible operation of the Haber-Bosch process that allows a varying production rate is demonstrated to be essential by some studies. However, the flexible ammonia synthesis is not widely implemented due to some technical limitations, because the existing control strategies in open literature allow only up to 10% variation of the reactor load, and even though some companies are actively investigating the technologies enabling green ammonia, dynamic green ammonia production, these technologies are usually protected by patents. So our goal is to address the control problem of the green ammonia synthesis under a wide operating range, saying between 50% and 100%. So here is a typical Haber-Bosch process. There are three reactor beds where hydrogen and nitrogen are converted to ammonia at a temperature above 600 Kelvin and a pressure around 200 bar. And since the reaction is exothermic, there are these quenching streams between each reactor bed to cool down the temperature. And the outlet from the third reactor bed goes through two exchangers to cool down to a temperature of 313 Kelvin and a pressure of 196 bar and enters a flash tank where the ammonia is liquefied and separated, and the vapor phase is recycled and mixed with the fresh hydrogen and nitrogen and recycled to the reactor beds. The design and the catalyst properties are like this. They are adopted from existing work. So to model this process, reactor beds are modeled as plug flow reactors, and the heat exchanger is modeled as a countercurrent exchanger, and for the flash tank, it's assumed to be an isothermal process. These models are pretty standard, and they're adopted from the existing works. Now for the control problem of the Haber-Bosch process, we want to control the inlet and outlet temperatures of each reactor bed because these are the key to have a high conversion. And we also want to track the pressure and liquid volume in the flash tank to have a desired ammonia concentration in the product. And also we want to guarantee the pressure in the flash tank is within the safe operating range. And finally, we want to track the recycle flow rate so that there is a desired amount of hydrogen and nitrogen reacted in these reactor beds. And as for the manipulated control inputs, there are 7 valves located at these places with the associated variables to be the split ratios between these feed valves. There is a vapor phase and liquid phase output flow rate of the flash tank, and there is a purge flow rate. So here we propose to use a nonlinear model predictive control scheme to address the control problem. And this is how it works. So we assume there is a varying feed flow rate of hydrogen and nitrogen due to the intermittent renewable energy sources. And for each of these different feed flow rates, we solve a steady-state optimization problem to obtain the optimal set points. And with these set points and the values of the real-time values of the state variables and the actions obtained from the ammonia plant as the initial condition, we solve an NMPC problem to get optimal control actions. And we implement these actions for the simulation of the ammonia plant for a period of time. And after that, we resolve the NMPC problem with the new values, the new initial conditions, and get updated control inputs. So for the steady-state optimization, we want to maximize ammonia production rate, and is subject to the constraints like the steady-state process model and the bounds of the state variables and control actions. Where for the NMPC, here we are trying to minimize a sum of a few terms over the prediction time horizon. The first term is about set point tracking, where the x hat is the controlled variables and xsp are the set points, and qx is a matrix of the coefficients. And in the second term, we are penalizing the action changes. So the ut is the manipulated control inputs, and qu is a matrix of the coefficients. And the constraints include the process model, which is a dynamic model, and we have ramping constraints set for the state variables. So because the drastic change of temperature and pressure can cause damage to the catalyst and the vessels. So for temperature, it is limited to be less than or equal to 0.5 Kelvin per second. And for the pressure change, it should be less than or equal to 0.1 bar per second. And also we have ramping constraint for the control actions to represent the valve properties. So for the split ratios at the feed streams, it can be adjusted by no more than 2% per second. And for the liquid phase and vapor phase output flow rate at the flash tank, it can be adjusted by no more than 1% per second. And there are also initial and terminal conditions and the bounds of the state variables and control actions. So for the setup of the NMPC, the prediction time horizon is set to be 180 seconds, which is 3 minutes. And each time, the decisions for the first 30 seconds are implemented. And after that, we solve the NMPC problem from the 30s to the 210 seconds, and still we implement for the first 30 seconds, and so on. The discretization, the time is discretized with a step length of 10 seconds using the backward Euler method, and the NMPC problem is formulated as a nonlinear program in Pyomo, and it's solved using the IPOpt solver. So for the case study, here is a feed flow rate schedule we consider. It lasts the test lasts for 5 hours, and it starts with a reactor load of 50%, and this feed flow rate change once per hour, and it ranges from between 50% and 100%. And we also add disturbances to the reaction rate at this WT, which is normal distributed. There is the standard deviation is a parameter we can adjust. So for sigma equals 1 means there is no disturbance, and sigma can also be 10% or 20% of the reaction rate, representing the medium disturbance scenario and high disturbance scenario respectively. Okay, so here is the result. So the temperatures at the outlet of the reactor beds can reach a steady state within 20 minutes after a transition of the feed flow rate. And during this transition, all these temperatures are maintained within a reasonable operating range, that the catalyst will not be deactivated. And we can also observe some small offsets between the temperature values and their set points. These offsets are most likely due to the numerical disturbances between the simulation of the process and the NLP problem solved for the NMPC problem. But these offsets are very minor, and they are less than 1% of the set points. And if we compare across different cases with different disturbance levels, with the increase of sigma, we note there are more fluctuations in the temperature values. But these fluctuations are also very minor, and they are still around the steady state. For the pressure in the flash tank, the slowest transition of the pressure can take around 40 minutes to finish, which is slower than the transition of temperatures. And here we set the safe operating range of the pressure is between 190 and 200 bar, and all these pressures are within that range. And we also observe that when the pressure gets a bit high and approaches the upper bound, the purge valve is opened temporarily to release the pressure, and when the pressure gets back to the steady state, the purge valve is closed, which is as expected. And finally, the most important is the ammonia production rate and ammonia concentration in the product. So here I'm showing the high disturbance case, and we can see that both the production rate and ammonia concentration stay very close to the optimum values dictated by the steady state optimization. And finally, we made a comparison with the PID control. So this is a pretty standard PID control architecture, and this is adopted from existing work and slightly modified. It is implemented in the Simulink. And here, if we take a look at this yellow line, which represents the temperature resulting from the NMPC control, compared to these blue dashed lines from the PID control, it is 3 times faster with the NMPC to track the temperatures, and it also shows much less oscillations. And also for the flash tank pressure and ammonia production rate and concentration, with NMPC, these controlled variables have are significantly faster and show much less oscillations with the NMPC compared to the PID control. So the key takeaways, we propose the NMPC scheme for the Haber-Bosch process with a varying reactor load between 50% and 100% of the nominal capacity. And with NMPC, it takes less than 20 minutes for the temperatures and 40 minutes for the separation pressure to reach steady state after transition, which is significantly faster and show much less oscillations compared to the PID control strategy. And finally, the ammonia production rate and concentration stay very close, and I would say almost at the optimum values dictated by the steady state optimization. For more information, you can see our published paper, and the source codes are available on GitHub. And I'd like to acknowledge the state of Minnesota for supporting this project, and thank you for your attention.